The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, please stop with your homework here, and we'll start. The first real lecture on how to use numerical methods on partial differential equations. So just a reminder of the last lecture, we looked at partial differential equations in general, right? We looked at the behavior of a few simple differential equations where we know how it behaves. We look at advection equation where the solution just keeps moving towards the right, right? We look at a diffusion equation where the solution just diffuses out, it becomes a flat line afterwards. We also looked at Burger's equation, which is the equation that can generate shock waves, where the characteristics converge together, they generate shock waves. When they diverge from each other, they expand, the solution expands. And we've used a little bit of human kind of animation to really animate the solution of these partial differential equations. All right, so this is a good intuition on the analytical behavior of the differential equations. And so try to remember last class, because in this class we are going to be using finite difference to solve them. And I'm going to ask you whether the solution I'm plotting on the screen is correct or not. I mean, not all of them are going to be giving us the right answer, as you already saw in the ODE section, right? And some of them are going to give me, in this case, answers that are correct in some part, but not really correct in other parts. And I also ask you, like, which part is correct, which part is not correct. Okay, so let's first start with a finite difference approximation, in this case for partial derivatives. So let's look at the simple case where my solution u is a function of x and t. What are the partial derivatives? What is a partial derivative? du dx and du dt, right? Why do we call that partial derivative? Because when we are taking derivative of one variable, we are holding the other one fixed. So in finite difference method, a good way to construct the grid, to say, I think it's the first time we look at the grid, is to actually construct the grid such that it is aligned with one of the variables. So that if you look at a particular direction on the grid, one of the variables are naturally fixed. So we used, in the last lecture, if you remember, we used these two axes, x and t, to visualize the solution, right? Now let's use the same plot in one direction x, the other direction t, to visualize my mesh. I'm going to design my grid or mesh to be like this. I think in finite difference, it's more commonly to use the word grid. And when you go to finite volume or finite element, we'll use the mesh instead, and you are going to see why that is the case. So we have a grid like this. And you're going to see that I'm discretizing both space and time separately. Okay, I'm going to call this, this x is equal to 0, this is delta x, 2 delta x, 3 delta x, 4 delta x, etc. And my time step is 0 delta t, 2 delta t, 3 delta t, etc. Right? So I have my solution sitting on this grid. And for example, here my space is equal to, I'm also going to assign my grid points. So this is what I call u of 4 and 1, 2, 3, 4, 5. So remember this notation. My subscript denotes the spatial grid point. and my superscript 5 denotes which time step I'm on. And here would be U of 4, 4. Here would be U of 3, 5, etc. Right? Okay, so now I have the solution. I have the discretized solution living on all these grid points. How do I approximate the spatial derivative of x at some grid point I at some time step n? Any suggestions based on what you learned in finite in ODE? Taylor series, yes, but like, can somebody give me a suggestion of what should I use?
That's 1 delta x further.
1 delta x further towards the left or right? Okay, let's try use right. Okay, so I can nope. If I can approximate the partial derivative by, in this case, I'm fixing n, right? In partial derivative, I fix the other variable. In this case, I fix n, which is the same as fixing t. I took the difference in the x direction, in the I direction, which is also in the x direction. So this is an approximation of the derivative in x. I can call this forward in space. Right? Okay, I can also, let's see, I'm going to insert a page. Landscape, it turns out I want smaller than A4. Well, this is good. Okay, I can also do backward in space. Backward in space, I would get UIN minus UI minus 1n over delta x. So this is backward in space. We're going to see as forward Euler and backward Euler have different stability properties, this is also going to have different stability properties. And I can also do a central difference. So central difference would be U of I plus 1, that is towards the right, minus U of I minus 1 towards the left, divided by how much? 2 delta x, because that is the spacing between them. So this is central in space. How about time? We also need to discretize time, right? We also need to discretize partial u, partial t at I and n. How do I approximate that? Exactly the same way as we did in ODEs, right? And we can approximate it as u of I n plus 1 minus u of I n divided by delta t. And that corresponds to what scheme we use in ODEs. This corresponds to forward Euler. And we are going to see later on what other schemes we can use. All right. So let's try to implement. Let's try to implement one of the combinations. So which one? I'm going to use forward Euler in time because that's really the simplest time integration scheme I can implement. Anyone vote for one of these? Huh? What? Central in space one. All right, good. Because you guys probably can do Taylor series in your head and figure out the central difference is actually second order accurate. It is better than the other two. So good. You have a good pick. Okay, so I'm going to go to MATLAB. The first thing I want to show you in MATLAB is actually, let me show you in the next class what's the difference between finite difference and finite volume. But I'm just going to show really kind of how a finite difference discretize a function. So when we have a function in space, we have to discretize it, right? So because the function is really infinite dimensional, we only have finite memory. So if you draw a function like this, finite difference only stores the values on the grid points. So the red circles are what it stores. What is in the middle are just forgotten by the computer. And all the derivatives has to be approximated by these discrete points. And this now seems natural to you for sure. But as we go to finite volume, we are going to see how different discretization schemes are going to be discretizing a function. Okay, so let's try to implement central difference plus forward order on the advection equation. Sorry, I haven't said what equation I'm going to do yet. So I'm going to implement it on this equation: partial u partial t plus partial u partial x is equal to 0, with a periodic boundary condition u at 0 is equal to u at 1. All right, so this is a periodic boundary condition. So this is the same equation as we tried to animate last Thursday. Anybody who goes out of this door comes back from inside here, right? So we should be seeing this is a linear advection equation, and all the characteristic lines are parallel. The characteristic lines are like the contour lines in the solution in the x and t diagram, right? So along each all the characteristic lines goes towards the right, and along each characteristic line, the solution is constant. Okay, so let's try to implement the forward order plus central difference and see how the solution looks like numerically. So I'm going to new a file, it's a script. So central space forward time. All right. So this is my central space forward time. I'm going to set up my number of grid points. Let's just use 100 grid points in space. Okay, and because I have a domain from 0 to 1, my delta x is equal to 1 divided by n. So this is my delta x. Let me choose the initial solution that looks somewhat like Gaussian. Okay, so that we have a peak and we see how the peak evolves. So let me first of all set my x equal to 1 to n times my dx. So I have a grid. And x is the spatial location of the grid. And let's set my u0, my initial condition, to be exponential of minus x minus 0.5 square divided by 0.1 square. And divide, I have to do this divide. Okay, so we can take a look at how the solution looks like. We can plot x and u0, and we are going to run the script to see how the solution looks like. So this is the initial condition, right? We have a Gaussian curve. The shape of the curve is exponential of 1 minus x minus 0.5. So 0.5 is the center of the Gaussian. And the width of the Gaussian was the standard deviation is 0.1. So this is like the standard, the width of the Gaussian, or half width of the Gaussian. Right, any questions on this? Nope. Okay, so let's decide on the time step. What do you guys want on the time step? 1.1. All right. Okay, let's go for I goes from 1 to 1 over dt. So let's simulate it for 1 time unit, because after 1 time unit, the solution, the speed of the solution going towards the right is 1, right? That is because in my equation I put if there should be a small c, then this c is equal to 1. So my speed of the solution going towards the right is equal to 1. So after 1 time unit, the solution should go through the domain once and end up exactly at the same location as the initial condition, right? Now, when I'm doing forward OLA plus central difference, I need to first compute DUDX at each grid location. And DUDX is, at each grid location, is the difference between the solution towards the right minus the solution towards the left, divided by 2 delta x. And look carefully at how I'm computing the solution on the right and on the left. DUDX is equal to what I'm going to do is I'm going to do a circ shift of my U0 of my U. I'm first going to say U is equal to U0. I'm going to do circ shift of U, and I'm going to be shifting 0 on the first dimension and a -1 on the second dimension. So what does this give me? I'm going to go back to MATLAB and tell you what it gives us. So if I do if I do 1 to 10, for example, I'm going to get an array going from 1 to 10, right? If I do circ shift of 1 to 10, I'm going to shift it for 0 in the first dimension and 1 on the first dimension. This is what I'm going to get. I'm circularly shifting this 1 to 10 towards the right. So instead of 1 here, I get 10 here, which is like this person, the 10 person comes out of the door and came into here, right? And the 1 person now is up here, the 2 person is up here. Everybody shifts towards the right for 1. Now, if I want to grab the I plus 1 person at the I place, this is like the opposite of what I need to do, right? What I need to do is I need to put -1 here so that at the first place, I'm going to be grabbing the solution, the next grid point. And particularly at the last grid point, I'm grabbing the solution towards my right, which is actually the other way across the door on the leftmost, which is 1, right? So this is the way to construct UI plus 1 if you have periodic boundary condition. What about UI minus 1? This is my UI minus 1. This is my UI plus 1, right? Any question on that? Some of you look backward. Yeah, on this one, things are being rotated towards the left. The 1 which is here now comes towards the end, right? And the 2 which is was here now comes here. 3 was here now comes here. Yeah. So in the ODE part, why didn't we do a circ shift? Okay, the answer is in the ODE part we didn't do a circ shift because we don't have the solution at end yet. So when we are at the end time step, we don't have the solution at the n plus 1 time step. While in the PDE part, we have a grid like this, and we are given the whole initial condition. So we're given the whole initial condition at t equal to 0. So we have all the data at this concept. Now our job is to go from this concept to this concept. We want to compute, run the solution here, all the solution on this point. And then we go forward and forward and forward. So there is a fundamental difference between space and time. In time, you don't know what is going to happen tomorrow, right? In space, we have access to the solution at all the spatial locations at the current time step, and if you store the past time step, also at the past time step, you know all these solutions. All right. So that's the difference between space and time. Although doing Taylor series analysis on them are the same, but in terms of coding, they are different. In terms of the order of computation, they are different. Okay, so going back to our MATLAB code, we shift towards the -1 direction, that is grabbing UI +1. If we shift the whole thing towards the +1 direction, we are grabbing UI. And if we divide that by 2 times dx, we are computing du dx, right? Okay, so now we have du dx. We want to plug this into this equation. Du dt, in this case, is equal to minus of du dx, right? This is what this equation is. If you shift du dx towards the right-hand side, du dt would be equal to minus of du dx. So that's what we are going to do. Du dt is equal to minus du dx. We used the partial differential equation to convert a spatial derivative into a time derivative. This is the result of using the partial differential equation, right? So the first step, find a difference approximation of the spatial derivative, the partial derivative in x. Use the differential equation to get the time derivative. And anybody wants to suggest what to do next? Are we back into the ODE world? We are back into the ODE world, right? We have computed the time derivative of the solution at all the grid points we have. We can use forward-Euler. We can use Wang, we can use trapezoidal or other fancy things we learned in the ODE section, right? So let's do the most elementary thing and apply forward-Euler. U is going to equal to U plus dt times du dt, right? This is exactly how you implement forward-Euler in ODE. And okay, so we already plotted solution at the initial condition. Let's also hold on so that we don't lose the plot of the initial condition, and also plot my x and u at t equal to 1. And let's see how the solution will look like. And let's actually plot this in red, because the initial condition is going to be in, let's plot the initial condition in black and the solution in red and see how it looks like. All right, we get a pretty big solution, right? Okay, this may not be the fault of spatial derivative though, because we know forward-Euler has a pretty limited stability region, right? But we know forward-Euler is zero stable, which means what? Which means it is always good to shrink the time step, right? Which means it's globally accurate, and the global accuracy means when you make the time step smaller, the solution of the ODE at least converges to the analytical solution of the ODE. So let's see if it helps in this case. Let's make delta t equal to 0.001. All right, and let's run it again. Let me close all before I do the plot. All right, this time we get pretty good, right? We do see the solution having a pretty good match with the analytical solution. And let's also visualize how this thing progresses. For every time step, let me actually do the plotting. For every time step, let me do the visualization as CLF, which means clear the figure. I'm going to plot the initial condition. I'm going to hold on, and I'm going to plot the solution. Oh, oops, my end shouldn't be here. So I'm clearing the figure, plotting initial condition, plotting the solution, and I need to do draw now. So let's take a look at how. Let me actually pause for a little bit, pause for 0.01 seconds, so that we can actually see the solution moving. All right. Okay, so the red one is my solution as my time evolves from 0 to 1. So does it look like we are capturing at least the qualitative behavior of the analytical solution? Yes, right. Although it is not completely satisfactory because the magnitude of my analytical solution seems to be growing a little bit. All right. Right, and also another concerning point you have surprised is that the solution initially was all positive, and you can look at my analytical expression for the initial position. Right, this thing has to be positive. It's exponential of something. How can it not be positive? But like later on, it becomes negative at some point. So it overshoots and undershoots. Right. I mean, we are not going to be discussing this today, but like we are going to be discussing the reason of this error both on Wednesday. Professor Wilcox is going to teach on Wednesday, and on the error of this finite difference method, how to analyze this error and convergence. And another very related issue is stability. That is something we are also going to be discussing in the PDE section. But this class, we are just happy we got a solution. And we can also see that the solution is going to get better as I make my grade to be finer. Instead of 100, let's do 200. And we run the same thing. It's going to be slower, but like the rate of growth is going to be not as severe as in the 100 case. All right, we still get grow a little bit, but at least you don't really see the undershoot below 0. And it seems to be the black one better. Question?
Question. We have to compare this
Mm-hmm.
Why did we see that?
Right. So we did a comparison between. Actually, let me answer your question by first. So the question is on backward difference versus central difference. So what do we need to change here to make it backward difference? First of all, it just needs to be delta x, not 2 delta x, right? And instead of ui plus 1 minus ui minus 1, we have u minus ui minus 1. So we're just going to be putting u here. This is going to be backward difference. And when you run backward difference, well, yeah, we get a similar solution. But now, what does the solution do? Instead of growing a little bit, it decays a little bit, right? So, and we can see we have the same number of grid points. Backward, the difference seems to have like more undershoot than the overshoot of the central difference. And again, Professor Wilcox is going to discuss the accuracy of these two methods on Wednesday. All right. Okay. So this is a implementation of the central in space and backward in space finite difference scheme. And we also discussed in the last lecture how to solve what is the behavior of a diffusion equation when we have diffusion instead of advection. We have a differential equation that is like this: partial u, partial t equal to k times partial square u partial x squared, right? And we can even have a mixed differential equation. We can have a mixed advection and diffusion, right? So how do we approximate this term? How do we approximate the second order derivative? Now the second order derivative has a very concise approximation. So the second derivative of x at a particular grid point at a time step can be approximated as this, as u of I plus 1n minus 2uin plus u of I minus 1n divided by delta x squared. This is a very unlike the first order derivative. You have the choice of central difference, forward and backward difference. This is for approximating second order derivative. This is like the single most popular scheme we use, and it is very difficult to find a approximation that is as popular as this. And let me describe to you why this is the case. Okay, we are approximating the second order derivative. We are only using 3 points, right? The center, left, and right. And amazingly, this thing has second order accuracy, has very good accuracy. So, and you can show that by doing Taylor series analysis. U of I plus 1n can be expanded as u of in plus delta x times, in this case, the partial derivative of partial u partial x at in plus half of delta x squared of the second derivative of u at in. Okay, I'm going to be expanding more terms. Is the third order derivative times delta x cubed divided by 6. And I'm just going to write over here O delta x to the 4th. Now this is this term. I'm also going to be expanding this term. ui minus 1 of n is equal to ui of n. In this case is minus delta x, because the difference between the I minus 1th grid point and the ith grid point is minus delta x. The squared, the second derivative term is plus again, because we are taking the square of minus delta x. The third derivative is minus again, because we are taking the cube of delta x. And again, we have plus delta x to the 4th. Now we can start to see which term starts to cancel out. See, we have one of uin here, plus another uin here. Now we have minus 2 of uin. So this and this cancel together, cancels with this minus 2 uin. All right, this is one term. Another term is this and this is added up. So I plus 1, I minus 1 is added up. So the first derivative term cancels. The third derivative terms, instead of canceling, they add up. So they divided by delta x squared serves as an approximation of partial square u partial x squared. It is a consistent approximation to partial square u partial x. And usually when you have 3 terms, when you are playing around the coefficient of 3 neighbors, you can cancel up to 3, you can make sure 3 terms add up to what you want to be, right? You get rid of the constant term, you get rid of the first order derivative term, you make sure that the second order derivative turns out to be what you want to approximate. But in this case, you get a bonus. The third order derivative term cancels out too, just by accident. And now you only get a delta x to the fourth, which after dividing by delta x squared, you get a second order accurate approximation to the second derivative. Right? So the error, which is the actual second order derivative minus the finite difference approximation, goes like O delta x squared. And this is a pure luckiness. Any questions on this? This scheme is what we are going to be using. Okay. Now let's go back and modify our code to also do second order derivative. So we have du dx, we have d squared u dx squared equal to, let me copy this, and we have ui plus 1, which is the shift of u towards the -1 direction. We minus 2 times u and plus u of I minus 1, and divided by delta x squared. So this is our second order derivative. If we want to solve the diffusion equation over here, the du dt would, instead of be minus du dx, we have the positive of d squared u dx squared. And let's put a kappa here, 0.1 of 0.1 kappa, so that it diffuses lower. And let's look at how the numerical solution looks like. Let's change back to 100. Oops. Again, it's the instability coming up. Let me make sure we have a small enough time step. All right, so we can see the solution of this PDE agrees with the analytical behavior of the PDE, which is the solution diffuses out. It becomes less sharp. And we can even combine these two terms. We can do a du dx plus this, right? We can do a convection diffusion equation. Let me cancel this. And we can see the solution diffuses, and also in this case it's shifting towards the left because I think the right convection diffusion equation should be minus du dx. Let me make sure that is the case. So okay, so we have a solution that is diffusing by the diffusion term, and also advex towards the right by this advection. All right. Okay. Now let's take just a 5 minutes break before we go to the matrix form. We did finite difference simulation. Before we go into the matrix form of this finite difference method, and you're going to see the matrix form is going to come up a lot, and it's going to be very useful in, for example, implicit schemes of finite difference methods. All right, okay, let's continue to the really fun part that you haven't seen before. That is, as we said, unlike discretization in time, you only have one step of information, right? You can only do things one step at a time. You don't really know what happens at tomorrow, what happens at the next time step. So you have to go one step at a time. In finite difference, when we discretize things in space, we actually have much more data than we have in ODE discretization, because we have the entire time step. At every grid point, we have the solution in our hand. Okay, that makes it possible to write the finite difference in a matrix form. Okay, so when we write the finite difference in a matrix form, we first need to write our solution in a vector form. We know our solution let's say we know our solution U at the first grid point, U at the second grid point, U at the nth grid point. We have them all, right? So that is what we have. Can we compute, not D, but partial U, partial X at the first grid point, partial U, partial X at the second grid point, etc., partial U, partial X at the last grid point? As a joint matrix, I said joint matrix because sometimes when you have, let's say, 1,000,000 grid points, how big is the matrix going to be? It's going to be a 1,000,000 by 1,000,000 matrix, right? It's going to be a 1,000,000 by 1,000,000 matrix. Think of n is 1,000,000. And this is why, I mean, I don't know if some of you have heard of the term sparse matrix. That is why sparse matrices are invented, because usually people don't have enough memory to store like this 1,000,000 by 1,000,000 array, right? I'm going to talk about that later, but like sometimes you have this joint matrix. Now, what is this joint matrix? What are the elements in this joint matrix? If it is a central difference, let me write down the central difference formula here. Let me write it here so that it's go down to here. No, okay. In a central difference, partial U, partial X at I is equal to U of I plus 1 minus UI minus 1 divided by 2 delta X. And let's assume again we have periodic boundary condition, so that if I is equal to n, then I plus 1 would be equal to 1, right? If I is equal to n, if I is the last grid point, then your neighbor towards the right is actually the first guy on the other end, right? So n plus 1 is like equal to 1. Now, what is the first line of the matrix with that periodic boundary condition? What happens if I want approximation of PDEs at 1 when I is equal to 1? Yeah, I have 0 here because this formula do not depend on U at I, right? Now, when I go to the second one, what is the multiplier on U2? The multiplier on U2 is 1 over 2 delta X, right? And is there any other non-zeros? All the way up to the end, where because I have periodic boundary condition, I have this, right? Okay, how about the second line? The second line is actually easier. Try to do it. When I is equal to 2, when I is equal to 2, du dx at 2 is equal to what? It's equal to U3 minus U1 divided by 2 delta X. So U3 and U1, which is this and this. So this guy is non-empty, this guy is non-empty, right? We would get minus 1 over 2 delta X here because U1 is being minused and U3 is being plussed. So we have 1 over 2 delta X over here. We have 0 in the middle, 0, and 0. Everything else is 0. So as we are going to see, for each line, there is only going to be 2 non-zeros. Only 2 non-zeros, because each derivative only depends on 2 neighbors. That means each line only have 2 non-zeros. If you have more terms over here, then there are going to be more non-zeros. Right? 2 terms means 2 non-zeros for each line. And for the third one, my minus is going to be operating on U2. My plus is going to be operating on U4. And for the fourth line, my minus is going to be operated on U3. My plus is going to be operated on U5. And etc., etc. So the diagonal is always 0 towards the very last line. The subdiagonal is always going to be minus 1 over 2 delta x until the last line. And the upper diagonal is always going to be 1 over 2 delta x. Am I missing something here? For the last one, the positive is over here because of the periodic boundary condition. Yes?
Oh,
Exactly. Because we are assuming a periodic boundary condition, this point, instead of lying over here, there is no longer anything towards the right anymore. So it is actually the first element on the left. This entry, remember how matrix multiply with a vector? This entry is going to be multiplied on U1, right? Instead of U and last one, which is W6. Right? Any question on this joint matrix? So all of this matrix is maybe a million by million, but it only contains 2 million non-zero entries. Most computers have enough memory to store 2 million non-zero entries. All right, so this is central difference. Let's just do an exercise of how if we do a, I haven't talked about upwind yet, so backward in space difference. Huh? Towards the upwind of the characteristic. Good guess. Right. So if I do a backward in space, I'm going to be writing the same thing: partial u, partial x at 1, partial u, partial x at 2, etc. Partial u, partial x at n. I think I used the small. Yeah, I used the small n. Is equal to a joint matrix of the same size times U1, U2, etc. So nothing has changed except for the content of the matrix, right? And a backward space difference is partial U, partial x at I is equal to UI minus UI minus 1 divided by delta x. All right, somebody help me fill in the blanks. Fill in the blanks of a million by million matrix. Doesn't take that much time to fill in, actually. What is the first top left entry? 1 over delta x. It is no longer 0, right? Because the du dx at I actually depends on ui. In the last case, the du dx at I does not depend on ui. Okay, so we have one non-zero entry here because we have 2 elements in each derivative. What is the other non-zero entry? At the very end, that one is the same. All the others are zeros. How about the second line? We have diagonals to be always 1 over delta x because we always have 1 over delta x multiplied by ui. That goes into du dxi. And we have minus of 1 over delta x always towards the left because the value at the left is always multiplied by minus 1 over delta x. All right. Okay, another x. So how about let's try to in MATLAB try to construct the matrix form. When we construct the matrix form, we don't need to do it in every time step, right? We can do it well in advance. So after we set our initial condition, before we set our initial condition, we know what n is. We try to set up the matrix A. Okay, let's call it A DDT. So that is the matrix that gives me, DDX, that gives me derivative to x. Okay, so let me see what I did. Here is actually backward in space. So let's try to reproduce backward in space. This is the matrix I have. I already have delta x computed. Yes, I do. So then I need two matrices. One matrix, the first matrix is this guy. I need, first of all, this matrix. And somehow if I can add that matrix to the second matrix, if I can add that matrix to this matrix plus this little element over here, then I have the entire matrix, right? So let's look at the diagonal, the blue one. So can somebody tell me, is there an easy way to construct a blue matrix? Huh? It's identity matrix times 1 over delta x, right? That one is actually super easy. How about the other one? How about the black one? Yes, I can use diag. I can use diag if I don't have this one. I'm going to see later on if I have not periodic boundary condition. I mean, periodic boundary condition is actually good. Right? If I don't have periodic boundary condition, if this is non-existent, then diag is a very good way to do it. In this case, I'm going to use the same function, the circ shift, I just used to circularly shift the solution itself. I can also shift the matrix, right? I can take this matrix, shift it either towards the left or towards the bottom. It's the same way. I'm going to get the black matrix. Okay, it is equal to I of n divided by delta x. So that gives me the blue one. I'm going to minus I n by dx, but I'm going to circ shift the whole matrix by, let's do towards the bottom, right? Towards the bottom, it's 1 in the first direction, 1 in the I direction, 0 in the j direction. So I'm going to shift it by 1 and 0. Okay, that is my finite difference matrix. All right, now how do I apply it? How do I apply it? When I compute du dx, let me first do one thing. I want to make my everything to be a column matrix first, because by default, if I do 1 to n, it's a row matrix, right? If I want to multiply the matrices that way, I need my solutions to be like a columns. So initially I want to construct this by columns, and everything should be in columns. And this is no longer true anymore. I'm going to remove this. I'm going to just do a linear induction equation first. But my du dx is equal to a ddx times u. That's how easy it is to apply this finite difference matrix. Once I have the finite difference matrix, I don't need to do anything at each time step other than just applying the matrix just as if it is like a mathematical operator, right? I just think this matrix is my partial x. I apply it on top of u, I get partial u partial x. So this A serves like a mathematical operator. I'm going to run this. I'm going to get the same solution. Of course, this is backward in space. I get a solution that moves towards the right, but also decays. Right. So this is what I have as a backward difference, and I can modify this. So I'm going to comment this out. This is backward difference. I'm going to do central, and in the central, the difference is I need to circ shift both. I need to circ shift this in the opposite direction. And instead of divide by 1 delta x, actually let me let me divide this by 2 delta x. So this is going to be my central difference, right? Agree? If you look at this, I have one identity matrix shifted towards the right. I have another one shifted towards the left, right? So I get 2 matrices subtracted. I get the central difference. Let me look at does the behavior look like the same as the central difference? It does, right? I have a solution moving towards the right. It doesn't really decay at all, but like kind of grows a little bit. Because if the maximum occasionally gets greater than 1, the scale shifts down a little bit. All right. Any questions on the matrix form of these two finite difference operators? No. Whenever you need them, I'm basically constructing a finite difference operator just like a mathematical operator, just like the DDX. And when I need it, I can just apply it. Okay. The interesting thing is that the operator I have already contains the boundary condition, right? The operator I have here, the periodic boundary condition is encoded into the operator or encoded into A. If I didn't have periodic boundary condition, would I still have this? No, right? I wouldn't be able to say if I want to. I wouldn't be able to say if I want to grab the solution towards the left. I just need to grab the one at the right hand, right? I wouldn't be able to say that. So what if let's say we have a boundary condition at the left? What if it is not periodic? What if we have a boundary condition, let's say u at 0 equal to 1? Okay, so let's say u at x equal to 0 at any t equal to 1. This is consistent with our advection equation, because in this advection equation, the characteristics move towards the right, right? So if you didn't have periodic boundary condition, you need to specify the solution. You need to specify the solution also here and here, right? You need to specify the solution where the characteristics originate. You specify here as the initial condition when t is equal to 0. You also need to specify the solution here as a boundary condition. That is when x is equal to 0. Well, x is at the left end of the domain. In this case, it is equal to 0. Right? So this is the left boundary condition. All right. Okay. In that case, how do we deal with that? How do we encode that boundary condition into the matrix, into the matrix form of finite difference? Let's look at this. Let's take a look at the matrix, and the only thing we need to change is which row of the matrix we need to change. If we need to change one row, we only need to change the first row, right? Because all the other rows of the matrix are still exactly the same because they are the interior. Only the first row involves the boundary. So let's look at the first row. The first row has partial u, partial x at I equal to 1 at any n. Originally, it is equal to u of I minus 1, which is, in this case, is 0, right? Minus u1 divided by delta x. This is my backward, again. This is my backward in space. This, yeah, it's the other way around. Thank you. It is U1 minus U0. Yes. Okay. In the previous case, we said the domain is periodic. U0 is just UN, right? Now, what is the case that we have a boundary condition that is given to us? We know what exactly U0 is. We know that U0 is equal to 1. Then the derivative is U1 over delta x minus 1 over delta x. We have a term that doesn't depend linearly on the solution. Or if you look at the matrix form, we have, first of all, this term goes away, right? We don't have this. But in addition to the matrix, we have something else. We have positive, we have a negative of 1 over delta x sitting over here as an additional vector to this matrix. Let me make a new page. Okay, I'm going to draw what the matrix is going to look like. When we have a boundary condition, my partial u, partial x at 1, partial u, partial x at 2, partial u, partial x at n is equal to a similar matrix minus delta x on the subdiagonal. I want to leave enough space for the vector I'm going to write. My U1, I think I use the big U for the solution, UN, this should be big U, plus something else. And that something else is going to be 0 almost everywhere, except for the first row, which is minus 1 over delta x. And it is going to be 0 everywhere because I don't need to modify anything. Right? This is, how did I achieve this? I plugged the boundary condition into the finite difference formula at the grid point that is close to the boundary. All right, that is a general technique of plugging in the value of the boundary condition into the finite difference field. Okay, so let's modify what we did onto here. So let's copy this. I think I should rename this as backward because this is backward. And I'm going to copy another one and say boundary condition, backward space, forward time. Okay, now that's correct. So what do I need to do? I need to change. Oh, okay. I need to change the operator, right? I need to change the operator to include the boundary condition. How do I do that? If you look at what the matrix is like, I still have the diagonal term to be exactly the same. I still have my identity of n divided by delta x. So that is this part. Now I also have my red part, which is not exactly a circular shift of a identity matrix. So here I'm going to use the function called diag. Diag of it's a function that you need to give me what are the elements on the diagonal and how much I shift it. Okay, if k is equal to 0, then the elements lie exactly on the diagonal. If k is equal to -1, I get exactly what I want because it's -1 shifted towards the it's -1 shifted towards the upper diagonal, which is 1 shifted towards the lower diagonal. So the elements would be 1's with n minus 1 elements divided by delta x. These are the values, and minus 1 towards the shift. Okay, so this is what the matrix is going to be like. I'm going to paste it here and take a look at the matrix. The 100 by 100 double. On the diagonal, it is 1 over delta x. On the sub-diagonal, it is minus 1 over delta x. Right? I get what I want, and I also don't have this. I don't have a minus 100 over here, as if I do in the periodic case. Now let's run it to see what we have. Okay, we still see this thing going over here. What happens on my left? Oh, okay. Did I forget something? I forgot the boundary condition. So I forgot to add the vector b when I apply this derivative. The end result is I have a boundary condition of 0 here. Right? I'm setting the boundary condition to be 0, and as you're going to see, as this thing advances towards the right, it is going to be no longer coming from the left. So yeah, I did forget something, but like we still have set a boundary condition that is not periodic, because you see this thing starts to go out, I'm still going to have 0 here. Okay, so let's add the b. My b ddx is going to be 0 n 1, and my b ddx, the first element, is going to be 1 minus delta x. 2 minus. All right. When I apply it, du dx is this plus b. All right. Yeah, this thing is still going towards the right, and it doesn't come back from the left. So now let's look at what if we do have a non-trivial boundary condition. We run it. What happens? Undefined functional variable b, so it's b ddx. All right, I'm gonna run it. All right. So we have a boundary condition of b equal to 1 over here. As you see, this is the behavior of the differential equation with the boundary condition. So everything advances toward the right, and of course the boundary there should be a discontinuity over here, but the numerical solution actually smoothes the discontinuity out, and you get a finite jump from 0 to 1 over here. But you see the boundary condition being enforced correctly, and things do move towards the right. All right. So the right way to put boundary conditions, one right way to put boundary conditions is to substitute the boundary value into the differential operator, into the discretized differential operator, and derive not only a modified matrix form, but also a vector that added on to the matrix form. Okay, so the question is, this form of the boundary condition looks like we are adding a source into the differential equation. And you are absolutely correct. In many, I think not only in this case, but in several other numerical schemes, applying the boundary condition is essentially adding a source, like right at the boundary condition. So sometimes like applying the boundary condition is knowing how to add the source onto the right-hand side near the boundary so that your numerical solution converges to the analytical solution with that boundary condition. All right. Did I answer your question? Is that? Well, so the effect I have is The effect I have is not due to the boundary condition, but due to the finite difference scheme. Yeah, the scheme is going to gives you truncation error. It is not going to approximate your first order derivative exactly, and that truncation error has an effect that smoothes out any discontinuities. I mean, the truncation error, you can actually see it. The truncation error looks like a diffusion term, right? It looks like it's diffusing your solution out instead of just advecting it. And the behavior of the central difference scheme is very different. All right. Okay. I'm just going to very quickly also gives you the finite difference form, the matrix form of the second order derivative, right? The matrix form of the second order derivative is if you have the second order derivative of u at 1 and the second order derivative of u at n, again is equal to this joint matrix. And again, let's assume it's periodic boundary condition, so we don't have to worry about the boundary condition for now. Okay, so the second derivative, partial u, partial square u, partial x at I is equal to 3 terms, right? We have a u of I plus 1 over delta x squared minus 2ui over delta x squared plus ui plus 1 over delta x squared, right? Kind of factored out the over delta x squared for each term. The same as the second order finite difference operator we wrote down. So ui plus 1 minus 2ui plus ui plus 1. Everything divided by delta x squared. Now, if we have periodic boundary condition, how do I put this into the matrix? Sorry? The derivative. Oh, the derivative. Yes, thank you. Yes. Yes. Okay. So how does this term go into that matrix? So let's start with the diagonals. The diagonals are all the same. They are coefficients on this term. This term goes into the diagonals. Let me, oops. Yeah. This term goes into the diagonals. Let me color that by blue. Is 2 over delta x squared negative, thank you, delta x squared all the way to here minus 2 over delta x squared. Now, where does this go? ui plus 1. It goes towards the upper diagonal. It goes over here. It's 1 over delta x squared, 1 over delta x squared, all the way to 1 over delta x squared. And here, 1 over delta x squared. Because when I is equal to n, I plus 1 is actually equal to, it's the same as u at 1. Okay. And lastly, let's fill in the, okay, let's fill in this I minus 1. This is I minus 1. Let's fill in the I minus 1 term we have on the lower diagonal. It's the same as the I plus 1 term. 1 over delta x squared, 1 over delta x squared, and 1 over delta x squared. The last, the first term is actually over here. It is, in order to get the second derivative for the first grid point, you have to grab all the way from the last grid point. Okay, so this is the matrix form of the second order derivative. Okay, so next class we are going to look at how how does finite different schemes converge as we make the grid point more and make the spacing smaller, and also start to look at two-dimensional problems. Right. Thank you.